So the derivative is the instantaneous rate of change of the dependent variable with respect to its independent variable. And certainly not always, but typically we think of our dependent variable as our y and our independent variable as our x. Now, lots of times they will use different letters. They use t a lot as that independent variable for time. They might have like s of t instead of x and y. But when you're thinking about your axes, it's your x-axis and your y-axis. So your units for f prime are the unit for f divided by the unit for x. So if you think about the way that we write derivatives, sometimes we would just do like a y prime, but sometimes we would do dy dx, and certainly we've talked about a derivative being a slope, which is your change in y over your change in x. So it's the unit for f, which is your function, that also can be thought of as your y coordinates, divided by the unit for the x, or your independent variable. Okay, so these first questions we're going to look at are only going to ask us about the units of our problem. A lot of times whenever they give one of those FRQs that's in context, it's going to say give units with your answer, and then one of the points in that problem is just going to be for having the correct units on everything. So our function C equals f of t gives the cost in dollars of running a piece of equipment for t hours. Okay, so it wants to know the units for f prime of t and f double prime of t. So let's start thinking about like our graph for c of t. We don't have any clue what it looks like. So this is f of t, which means this axis right here is t, and this is f of t. And it says that this gives the cost in dollars, so this is cost in dollars, of running a piece of equipment for t hours. So this is hours here. So if we are looking at f prime of t, it's the slope of that graph, which is your change in y over your change in x. So that means you've got units for your y-axis here, which would be cost in dollars, and you would have your x-axis here is your hours. So we would just have dollars per hour. So if you're finding a value for f prime of t, it's giving you the cost per hour for running that piece of equipment. Okay, so if we think about second derivative here, the second derivative is the slope of the first derivative, right? So let's think about if we have some sort of graph, who knows what it looks like, it doesn't really matter. If we wanted to be technical, I could try to make it match this one, but I'm not going to. That'll take too much effort. This axis is still t, because t is your independent variable. This is f prime of t, which means this is still hours. And if we're talking about f prime, we were measuring f prime in dollars per hour. So that y-axis is in dollars per hour. So if we are doing a second derivative here, then if we're thinking change in y over change in x, the y-axis here for f prime of t is measured in dollars per hour. So we have dollars per hour. And then x is hours. So the way I prefer to write this is dollars per hour per hour. I prefer this. Now, it is okay. Another way that this can be done, so what I've got is I've got dollars per hour divided by hours, which, if I make this a fraction, dividing fractions is easy as pie. I'm going to flip the second and multiply. Oh, wait, I flipped it. And so when I do that, I will get dollars per hour squared. So you could write it dollars per hour squared. This would also be okay. If you think about what this means, I don't think, have any of you guys had physics? I don't think so. Last year I had several kids who had taken or were taking physics, but this is essentially like acceleration. I don't know if in like, do you guys take physical science? Y'all don't take physical science, do you? You took chemistry instead? Yeah. So you may not know much about this at all, but this is kind of like acceleration. It's how fast something is increasing. So like this would be like your dollars per hour is just your simple rate of how many dollars it's costing per hour for that. This is the dollars per hour, so it's how fast that rate is increasing or decreasing. So it's like acceleration. This would be like your speed, sort of, and this would be like, or your velocity, I guess, and this would be your acceleration. I prefer for students to do dollars per hour, and the reason is because kids don't usually mess it up if it's dollars per hour, but when we have things like feet per hour, a lot of times kids will put the square on the wrong one. They'll do square feet per hour instead of feet per hour squared. So I prefer doing this one just for that reason, but they are equivalent, so you could do either one. There. All right, let's move on. Okay. The time it takes to run a distance d is given by the equation t equals capital R of d, where t is measured in hours and d is measured in miles. Okay, and so it wants to know the units for r prime of d and r double prime of d. So let's think about this one a little bit, because this one is a little bit backwards. Because in this case, what is our independent variable? It is not time in this case. It feels like it should be time because it's pretty much always time, right? But in this case, it is not time. It's distance. Your independent variable is always like what your function is written in terms of. So this would be distance in this case. Now, like you could write this scenario in the opposite way, where you have distance as a function of time. But the way it's given here, distance is your independent variable. So that means that on our graph, if we have whatever that graph looks like of R of D, that this is your D axis here, and this is R of D. And so D is distance, and D is measured in miles. So this is miles here. And R of D equals T, right? So R of D is the same as T, and T is measured in hours. So this is hours right here. So this is tricky, and this is why I like to draw that graph out. Because when I see miles an hour, my brain immediately says miles per hour is going to be the derivative. Because miles per hour is what we normally talk about, right? But it is not in this case. Because r prime of d is going to be what we're talking about, the change in our y-axis over the change in our x-axis. And what did we use to measure our y-axis? Hours. And for our x-axis, we have miles. So we're talking about hours per mile, which seems so backwards, right? So instead of talking how many miles you can go in 1 hour, we're talking how many hours it takes to go 1 mile. This is basically like your mile time, like your pace is kind of what you're looking for. Like if you, those of you who are runners, you could, like your watch tells you that, doesn't it? It'll tell you your pace, like how many minutes it's taking you to run a mile. Usually mine's several. I'm not running, I'll be walking, but this will be like your pace. So that is what we're looking at here instead of your velocity. Okay, so what do you guys think for second derivative? What are the units for that? Yes, hours per mile squared. Because what we'd be looking at right here, if we had r prime of d, this would still be d, it would still be miles. This would be r prime of d, which is hours per mile. So we would have r double prime would be our change in y over our change in x, which would be hours per mile per mile. So you can write it like that, hours per mile, or you can do hours per mile squared. I feel like in a physics textbook, you're more likely to see that hours per mile squared. However, for AP exam purposes, I feel like you're less likely to mess it up if you do the hours per mile per mile. Yeah. All right. Okay. This is a type of question that you'll get a lot. This one doesn't even ask you to figure out what it is. A lot of times in an FRQ, it'll ask you to figure out what it is. But we've got something like the length of a scarf is given by the function L equals S of T, where length, which is capital L, is measured in centimeters, and T is time, is measured in minutes. What is the meaning of S prime of 7? So a lot of times in a real FRQ, they'll give you the equation for S. They'll ask for S prime of 7, but they will ask you to tell what it means in terms of the context. And you'll get a point for doing the math, which a lot of times is not difficult math. And then you will get a point for the meaning, which is really the harder part of the question. So if we think about what we're looking at here, we got T would be our independent variable right here because it is what the function is written in terms of. So T is independent. What is T measured in? Minutes. Okay, centimeters is what our L is measured in, and L is the same as S of T. So whatever that graph looks like, that is measured in centimeters. All right. So units can help you so much on this. We have our units for S prime of T would be, again, change in Y over change in X, which would be centimeters per minute. Okay, so that helps us a lot whenever ask us for what S prime of 7 means at this point. So first of all, if we're doing S prime of 7, that is an instantaneous rate of change. It is not an average rate of change. It is not how much you have knitted the first 7 minutes. It is at that moment, right? So you would need to say, because this is 7, S prime of 7, you would need to say at 7 minutes, the scarf is being knitted at a rate. This is the rate. This has happened. Derivatives give you a rate of change, right? At the rate of S prime of 7 centimeters per minute. Now, if this was a real FRQ question, we'd probably figure out what that number was, and it might be 12. 12 would be really fast. 12 centimeters per minute would be super fascinating. Maybe if it was a machine and not a real person, but we would get, you know, a number for that. Since this problem didn't give us, it's just asking for the context, that's what we would have here. Okay, questions? Okay, here is one that does actually give us an equation. Okay, and we'll use our calculator on this. It could be done without a calculator, but since they got those decimals there, I'm thinking I probably intended for us to use a calculator. So this one's not asking you to interpret, but it's going to ask you the question so that you must interpret what's happening. So the equation H of T gives the height of water in a swimming pool at time T. The height H is measured in feet, and the time T is measured in hours since midnight. Find the instantaneous rate of change of the height of the water in the pool at 10 a.m. Okay. So let's think about this. What is this asking us for? Instantaneous rate of change. What does instantaneous rate of change mean? What does that mean we're doing? What are we finding? Derivative. So this is wanting H prime of T at what time? 10, and it tells us T is measured in hours since midnight, so 10 a.m. would be 10 hours since midnight. So H prime of 10 is what we're looking for. Now, if this is a free response question, you don't have to find H prime of T. And if it's calculator active, you do not have to find H prime of T. Now, you could. This is not a really difficult derivative right here, so you could, but you don't necessarily have to. So let's work with our calculators a little bit. So everybody grab your calculator. This particular problem I was probably making up myself, and usually the equation will be a little bit more complicated if they're making it a calculator active problem, but we can still get an idea of what we're doing here. So first thing, you don't have to do this, but I like to do it from y equals. So let's go to y equals and let's type in that equation. So and I'm going to use an X instead of a Now, you don't have to do it this way. You can type it all in just in the main thing, but I like to do this. Plus, if it is for response, a lot of times you're using that same equation over and over, so it'll save you some time. So let's go back to the home screen. Clear that out just so it doesn't get on the nerves. So we are wanting to find the derivative at 10. So I'm going to do F3, which is calculate, and it's going to say differentiate. Now, you've got two options here. Because I have put this in y1, I'm just going to type y1 of x, comma x, like that. Your other option is to type in the equation instead of doing y1 of x. Okay, so you're doing F3, you're going to pick differentiate, y1 of x, comma x. Now, I'm going to go ahead and hit enter here, but this is not how I want to do this problem for this. If you hit enter, it will find the derivative for you, and then you could plug in that number, but this is not the most efficient way to do the problem, because if this is a calculator active problem, you do not have to write that down at any point. So this will give you the derivative. Sometimes you may have something where it can't find the derivative. If it's a really complicated one, it can't do it, but it can do this one pretty easily. But we don't really care about what the derivative is. We just want to know the derivative at 10. So to put this into your calculator, you want to do derivative y1 of x, comma x, close your parentheses, and then there is a button here that is a straight line. It's right below your equal sign there, and next to the 7. And so that's your such that key, and you're going to do x equals 10, and it will plug in 10 for you. There. So if you're doing this problem, all you have to write is h prime of 10 equals 0.643. Go around it to 3 places. Now, you would need to give units for this problem more than likely. I didn't put that you have to here. So what would the units be for this? Feet per hour. Because your original T and H of T, here T is hours and H of T is feet. So it'd be feet per hour would be your derivative. So at 10 a.m., your rate of change of the water is 0.643 feet per hour. What's happening to that pool? Is the height of the water going up or down at that point? It's up, because this is positive. What would it look like if you had a leak, if it was going down? Negative. You'd have a negative right here.
I didn't even say that.
Jeremy's afraid to even say negative. Anyway.
I didn't say that.
All right. Okay, here's another one. Definitely calculator active. So let's go ahead and clear out what we did have. Let's go to y equals, and let's type this in. And this is very much like you will see a lot of times for a part of a free response question on the exam. They'll give you an equation. They're telling you from 0 to 50, and it's asking for S prime of 15 and S double prime of 15. It tells us this gives the weight of sand in a storage container after X days where weight is measured in tons. And it asks for S prime of 15, and using correct units, we're supposed to explain the meaning. So the math part, particularly if it's calculator active, is the easier part of this. So we're going to go back to the main screen. All right, who can tell me what buttons to push? Troy, what should I do? Yep, so what do I hit to get there? Perfect. All right, what do I type in now? Y1 of x. Good. Comma. X. Parentheses. Such that, which is that bar right there, x equals 15. Okay, so if I'm doing this problem, I don't need to write down any of the work because this is calculator active and they are assuming you're going to do that work on your calculator. You do need to write down s prime of 15. Don't just write down that number. You need to label what you have found, and you're going to say negative 5.527 there. Let's think about our equation right here so we can get our units correct. It's s of x, so this is x, this is s of x. What is x? X is not weight. X is our days. So x is days. And then s of x, so this equation gives the weight of sand, and weight is measured in tons. So this is tons. Okay, so this is tons per day. All right, what does it mean? So we're going to talk, now we need to talk about what's happening in the storage container. We need something else with that. When are 5.5 tons being removed every day? I would probably say at 15 days. After's probably okay. I think after is okay. After a little bit makes me think like the whole time up until 15. So at 15 days. So that's important. You've got to tell what time this is happening. So at 15 days, what's happening to the sand? Are we increasing or decreasing? We're decreasing because we have a negative rate right here. So the weight of the sand is decreasing by, now careful here, 5.527 tons per day. Now, notice I did not put a negative with that. Why did I not put a negative? Because I put decreasing, and decreasing covers the negative. What you cannot do right there, you cannot say that the weight is decreasing at negative 0.527. Because if you say that the weight is decreasing at a negative rate, you have a double negative there that is really like a positive, and it's incorrect. You can technically say that the weight of the sand is changing at a rate of negative 5.527. So if you say the word changing, that does not imply increasing or decreasing necessarily, and then you could use a negative rate. But the preferred way for you to do this is to, instead of using a sign for positive or negative, say increasing or decreasing there. That would be preferred because that really communicates that you know what's happening there instead of just using the changing at the negative rate. All right, questions there? Okay, second derivative. We need to find the derivative of the derivative, which I'm pretty sure we can do by doing this. That dy1 of x, comma x, that's all in the first line. So I'm going to do, I'm going to go to the very front and do derivative again. So I've got the derivative of the derivative. And then I need to put another comma x and another parentheses here. So I've got derivative of the derivative of y1 of x, comma x, close your parentheses, comma x, close your parentheses. Your such that x equals 15 still needs to be on the very end. If you put it before that, it's going to plug it in and you'll just get 0. And I think this is going to work. I might should hit enter before I... Yeah. And so everybody try that one. I'm going to walk around and make sure you've got it, because that one's a little trickier to get typed in correctly. You need another comma x in between that two parentheses right there. You have to do the comma x for the inside and the comma x for the outside. There you go. It's hard to see with that highlighted too. Let me go up here. See what I typed in a little bit. Alright, is it good? All right. So now I think the second derivative is so confusing to think about. Let's think about units for second derivative. If we're doing that, this is x, this is still days, but this is s prime of x. S prime of x, what we just did in A, that was tons per day. So, so when we're taking the derivative of this, we're going to have tons per day. Or you can say tons per day squared, if you prefer. So what you're doing with the second derivative is you're taking the derivative of the derivative. You're doing the rate of change of the rate of change. So you want to begin just like we did the last one. We're going to say at 15 days. That's important. You must tell, like when you're plugging in a number, you must tell at what time period or whatever that this means. So at 15 days, the rate of change of the weight of the sand is changing at a rate of. So the rate of change of the weight of the sand is, are we increasing or decreasing here? Increasing. At a rate of 0.276 tons per day So anytime you're doing a second derivative, assuming that the first derivative was just the amount, you're doing the rate that the rate is changing. Here, this was just a straight rate, right? We had S was the weight of the sand was changing at a rate of 5.527 tons per day. This is the rate of the rate. So if you kind of think of what's happening here, since our rate is negative at this point, right? Our rate is negative, that means we're losing sand, right? Amount of sand is decreasing. But is it decreasing faster and faster or slower and slower? Your rate of your rate is increasing, which means this number right here, like the next day would be like negative 5.2 something right here. So it is decreasing, but the amount of sand you're losing slowing down. The rate is slowing down here at that point. And that would be because you have opposite signs on these. So to me, that second derivative is a little confusing to think about sometimes. But if you think of it as rate of the rate, if you say rate twice in your explanation, that's usually a good thing to do. All right. Okay. All right. This one is a calculator problem, but it's not. Mostly just for convenience. Why is that not working? I want to let it go full screen. Okay. All right. So depth of water in a rain gauge is given by the twice differentiable function R for 0 less than t less than 25. R is measured in inches and t is measured in hours. Values of R prime of t, the derivative of R at selected values of time, are shown in the table above. It is known that the graph of R is concave down from 0 to 5. So at first it says, is there a time for between 0 and 24 at which the depth of the water in the rain gauge is changing at a rate of 0.5 inches per hour. So this is, well, first of all, it's twice differentiable, right? So that means that we can take the derivative twice and that we're continuous in this case. It says, is there a time at which the depth of the water in the rain gauge is changing at a rate of 0.5? So what would equal 0.5 here? Would it be R of t, R prime of t, R double prime? What's it asking? It wants to know that the depth of the water in the rain gauge is changing at a rate. Okay, rate would be what, Lydia? R prime. So what we're wanting to know, does R prime of t equal 0.5? That's what we want to know. Does it ever equal 0.5? And how can we prove it if it does? Intermediate value theorem. Very good, Joshua. This goes all the way back to the beginning. Because if I look at my numbers here, at 12 hours, my rate was 0. At 15 hours, my rate was 0.55. Did it have to pass 0.5 to get there? It definitely did. That only works if this is continuous, but they told us that R is twice differentiable. So we would say since R is twice differentiable, R prime of t is continuous. It is also differentiable, but for intermediate value theorem, it doesn't have to be differentiable. So if you say it, it's fine, but it's unnecessary. So, by the intermediate value theorem. You, without a doubt, in this problem have to talk about R of 15, because R of 15 is the only time you go above 0.5. You could use any of the other points on this interval because all of them are below 0.5. So it does not matter which one you choose. I'm going to use R of 12. So I'm going to say, by the intermediate value theorem, since R of 12, which equals 0, is less than 0.5, which is less than 0.55, which equals R. Oh, yes, thank you. R prime of 12, R prime of 15. There must be at least one time on 12 less than or equal to x less than or equal to 15 such that R prime of t equals 0.5. And therefore, R prime of t must equal 0.5 on the interval from 0 to 24. I'm not 100% sure if that last part of that statement is totally necessary, but it doesn't hurt to say it because they asked about the interval from 0 to 24. Obviously, 12 to 15 is on that interval, so it has to be included, but it might be good to put that last part with that conclusion there. So that's our intermediate value theorem. That's way back from the very beginning. It's just saying that if we were down here and we went up here, we had to cross this line in between, right? So we did that a lot. We were pretty good at it. It's easy to forget it at this point, but they love to throw that back in there on problems like this. Okay? All right, this is the same information from before. I just redid it on the next slide because every time I pull up a new slide, I need to see it. So we are supposed to use the data in the table to approximate R double prime of 16.5. Show the computations that lead to your answer using correct units. Explain the meaning of R double prime of 16.5 in the context of the problem. So we need 16.5. That is not on our table. How do we estimate a value here? What would we do with them? Those are the points we need to use. What do we do with them? We're going to find slope. Because this is R prime. It's asking us about R double prime. So we need to find the slope between those two closest points to estimate what the derivative would be. So we would say R double prime of 16.5. We will use squiggly equal signs because this is an approximation. It's not the exact value. And then we're looking at these 2 points right here. So we would say 0.4 minus 0.55 over 18 minus 15. And that's going to give me negative 0.15 over 3, which will give me negative 0.05, I believe. Did I do that right? I think so. Now, let's think about our units. What would units be for this? inches per hour squared. So inches per hour, or if you want to put inches per hour squared, that's fine. Again, the only reason I kind of like this better is because inches per hour squared is great. A lot of times students, particularly when you got inches, will do inches squared per hour. They'll square the wrong part because it makes sense to have inches squared. That's like an area, but it's not the correct units for this. So either one of those is good. All right, what in the world does this mean? Definitely important to put that at 16.5 hours. What is happening there? Okay. What is decreasing? No. The amount of water is actually increasing. Because R is our amount of water, right? R is measured in inches. That's our amount of water in our rain gauge. So R prime at this point, well, we don't know for sure that it's increasing, but probably it's increasing because we probably have a number between these two. Actually, we know we have a number between these two right here because we're concave down. But so we're we have a positive first derivative. So that would mean the amount of water is increasing, but we're getting a negative here. So it's not the amount of water that's decreasing. What is decreasing? The rate of change of the amount of water. So the rate of change of the amount, or I guess it's height, isn't it? Depth. Let's use the words they use. That's always probably of the depth of the water in the rain gauge. Is decreasing at a rate of 0.05 inches per hour. And actually it'd probably be good if we threw in approximately. I don't think they'd count off for that if you left it out, but this is an estimate, so it's approximately 0.5 inches per hour. So it's the rate of change of the depth of water is decreasing at a rate of, so the rate is changing at a rate. Second derivatives are confusing to me. All right, questions there? All right, we're almost done. All right, same information. At time t equals 2, the depth of the water in the rain gauge is 0.8 inches. Use the line tangent to the graph at t equals 2 to approximate the depth of the water in the gauge at 3 hours. Is the, let's see, do I even want to do this? What section is that in? Hold on just a second. I did this early last year, and I should have probably just done it early this year. Let me see where that shows up. I don't think it. It's 4.6. Do I even want to do it? Let's skip it. We're not going to do C. We're just going to wait till we get to C here. Okay. All right, so differentiable function E models the percentage of students who pass the 8th grade math exam in North Carolina for 0 less than or equal to t less than or equal to 50, where t represents the number of years since 1980. Find E prime of 15 and interpret its meaning using correct units. So definitely calculator active problem. I'm not going to have you do that one without a calculator. So go ahead and type that into your y equals. It's kind of hard to get it in right. And you're going to have to, so this is going to be, you're going to have 0.5 e to the, it's going to open parentheses, you'll have a 2. This sine squared, you can't type in sine squared. So what you have to do is you have to do sine of 0.1t. You got to close this parentheses, square it, and close one more parentheses. Plus t plus 50. Oh, it's so bad. Because you have to, that sine squared, you have to write that as sine of 0.1t squared. And you always, like, if it's not doing right, count, make sure you got 1, 2, 3, 4 open. So you got to have 1, 2, 3, 4 closed parentheses. Should look like this. There's a plus 50 over there on the end that you can't see. So, I check see if you got that in. And then the true test of whether you got it in correctly or not is going to be if you get the right answer. So once you get this typed in, it's not that difficult to find the derivative. It's just that same thing we do for the derivative. We're just going to tell it f3 differentiate y1 of x, comma x, such that x equals 15. And you should get this number, 0.603236. If you do not, something's typed in wrong. So e prime of 15 equals 0.603. There, so let's see how everybody's doing. Pretty good. All right. Maybe the hardest part of this might be getting it typed in correctly. The calculator's doing all your work on the derivative. It's not that difficult. You just got to write that down. Interpretation is, to me, the other difficult part of this. So let's talk about what this means. Let's do units first. So, we got like E of t. So we got t here. We got E of t. What's t measured in? That's years. And what is E measured in? Percent who passed. So passing. So our derivative, the units are going to be percent passing per year. So we've got to write a sentence for this. We've got to tell what's happening. Now on this one, I don't want to say at 15 years. What do I want to say? I would do in 1995. So in 1995, you could say something like 15 years after 1980. That's correct. It's just kind of a weird way of saying it, right? Because but you could say it that way and it would be correct. So in 1995, what is happening here? So this is just our first derivative. This is not a rate of a rate. It's the rate of whatever E is. What was E again? Percent passing. So the percentage of students passing the 8th grade exam or math exam in North Carolina was, okay, are we increasing or decreasing? Increasing. At a rate of 0.603% per year. Okay, questions?